probability and statistics for week number 9. Applications of normal distribution. The last class we have seen some problems which are direct application of normal distribution. Anyhow, the chapter has been given here as 6.4. We will see at least one problem in this case, and then we'll move to approximation of normal distribution to the binomial. And we will see two new distributions for continuous case called gamma and exponential. They are related. And then we end up with the random sampling, some introduction to sampling techniques. Fine, let's start. So here we have the tables, normal tables useful for solving the problems. You don't need to go back every time. So first one is for our negative values of z, and second one is for our positive values of z. Now we start here the application of normal distribution. A company pays its employees an average wage of $15.9 an hour with a standard deviation $1.50. If the wages are approximately normally distributed and paid to the nearest cent, what percentage of workers receive wages between $13.75 and $16.22 an hour inclusive? That's right. We are dealing with a direct normal distribution, no approximation here. Normal distribution. And now percentage, case A. See, from the question we have to collect the information. Read the question. Average is mu. This is your mu. So write down, we have mu. Mu is 15.9. 0 in second place. No. Standard deviation is 1.5. Now what is the question number A? What percentage? Find probability and multiply by 100. That is percentage, isn't it? Percentage is the different version of probability here. What percentage of workers are between? So the question is probability of X lies between. Probability of X lies between 13.755 and 16.22. This is what the question. Now, for X is equal to 13.5, we need to find a Z value, of course, for 16.22. So, what is the formula that connects Z and X? Z is equal to X minus mu over sigma. So, if X is 13.75, what is it set? Is equal to 13.75 minus mu. Mu is 15.9 over 1.5. Use your calculator. You will end up with a negative 1.433. We want only two digits, negative 1.437. That is our Z1. You can take. What is Z2? For second value of X, 16.22 minus 15.9 over 1.5. Use a calculator. You will get it as 0.2133 is enough to write two digits. Table permits only for two digits after then dot. So we have two Z values. Now the question number A says that this is probability of X lies between 13.75 and 16.22 is equivalent to I'm writing on the top. Probability of Z1 is negative 1.43 less than less than 0.21. So area lesser than area to the left of 0.21 minus area to the left of negative 1.43. How do you find it? Um, on the normal curve, the negative value will be here. It is Z1. Positive value here is Z2. So the area between them can be found by using first find by using the technique. First find the area up to Z2 left of Z2, and then subtract the area to the left of Z1. So you will find the area of this part, isn't it? So this is what we are going to do again. Let's from the table find what is the area to the left of 0.21 positive, isn't it? Go back to some positive. Point 0.2 is here. 0.2 is here. 0.01 is here. It is 5832. So first area writing here, probability of z less than 0.21 is 0.5832. And now find the probability of z less than negative 1.43. Go to the negative page. 1.4. Where is negative 1.4? Negative 1.4 comes here. Next value is 3. So 0.3 is this column. This column is 0.3. It is 0.0764. So we will write it next 0.0764, which is here 0.0764. So subtract this one from this one. That will be your answer. Okay? So we can write the answer of this problem here. The answer is, let me write some part. The answer is 0.5832 minus 0.5832 minus 0.07664. When you subtract, you get 0.5068. Right here. It is 0.5068, approximately 51%. So when you multiply by 100, you will get the answer is 50.68%. So the 6 is smaller than 5. You can write the answer of question number A is 51%. Now let's deal with case B. Case B, problem number B. Highest 5% of the employee hourly wages is greater than what amount? Highest 5% is the normal curve. The highest 5% falls right at this is mid value mu is 0, isn't it? And you take some z here or x here, isn't it? X gives z, z gives x here. And this is the 5%, highest 5%, 0.05. Okay, no. 0.055 percentage. When you divide by 100, you will get 0.05. The area above beyond z, above z, the right of z is 0.05. Obviously, what is the area below z? It is 0.95. 1 minus 5%. So 95%, isn't it? So 95 is 95.95. So to the left of this curve, z value, the area is 0.94. So the area is given now. This area is 0.95. It will be a 4-digit value, 9500. So find z, and then by using z form value, find x. Z is equal to x minus mu over sigma. We know mu and sigma for this problem. We need to find x value by using the z value. So if area is 0.9500, find z value. So area is 0.590. So z lies in the positive direction, positive side. Isn't it? Go back to the positive table. Here. 95 area is 0.9500. So look for 0.9500. What is it? 0.9500. 9545, 9505. Both are equally distanced from 9500. Obviously, the choice is this one. You can even choose this one. Nothing going to be wrong, right? My choice is 0.9505, very near to 9500. So from left side we will get a 1.6. From the top we will get a 0.5. The value of z is positive 1.65. 64 is also valid. Okay, can type. So z is 1.65. Go back to this table, this problem, and then now find z value. If z value is given, z is 1.65. So what is x? If it is 1.65, x minus mu is 15.9 over 1.5. So multiply this one here, 1.65 times 1.5, and there will be negative 15.5, 15.9 the left side. Add it to the left side, 15.9, which is equal to x. Find this one using calculator. It will be 18 point. So the answer for x is 18.375. That's the answer, 37. So 18.375, the exact answer of part B. That's it for this problem. Now we go to the next topic. So this kind of problems we have already seen for normal distribution. So we have chosen only one problem for application. You can find such a problem from textbook. There are exercise problems and example problems as well. Practice them. Now we go for approximation, normal approximation to the binomial. What we are going to do here is x is a binomial random variable. When you are dealing with the binomial random variable, you will get two different information: size, samples. I mean, number of trials or the size, n, and probability of success. These two are the parameters of binomial distribution, NP. So if you know NP, you can find mean. Mean is n times p. So for normal distribution, we need, and remember, very important information is binomial is a discrete probability distribution, but normal is continuous. So when we approximate a discrete division by using a a continuous distribution, there will be certain errors. To avoid some errors, we will do some small works in this case. We will see. So we can easily find mu and the sigma what we need for normal distribution. For using the normal curve, we need two information: mu and sigma. Sigma is square root of variance, and we know variance for binomial distribution is np cube. So under square root is np cube. This is under square root is np cube. This is sigma. And what is q? If you know the probability of success, q is 1 minus p. So all terms are known. To find mu and sigma so that we can directly use the formula of Z, and then use Z table. Assume that a sample size is n is very larger, then this becomes a normal standard distribution, standard normal distribution with mean 0 and standard deviation 1 with a new variable Z. Okay, so for a binomial distribution, we will get n and p. By using n and p, find mu, and using npq, find sigma. Use in this formula, and there are some more works coming. To illustrate the normal approximation to the binomial distribution, we draw a histogram. For binomial distribution, the sample size, that is the number of trials, has been given as 15 n, and the probability here n is 15, and the probability of success is 0.4. You notice n is somewhat bigger. You can, in problems, it may go to hundreds and 200s and 400 thousands is possible. Probability will be somewhat near to 0.5. And then superimpose the particular normal curve for the same problem, both on the same graph, having the same mean and variance as the binomial variable x. Now we will check what is happening. This is the given binomial distribution. By using this binomial distribution n and p, we are finding mu and sigma for normal distribution. This is sigma square is 3.6. So we can find the sigma by taking the square of it. Okay. Now the histogram for this one. What is this histogram? For every x value, they will find probability, and against x, the probability is considered to be y-axis. They will draw a box diagram, that is histogram, the corresponding. So this can be done by using SPSS. Now I will show you this histogram for this binomial distribution. The boxes, the rectangular boxes represent the binomial distribution. For x equal to 0, probability is 0 near to 0. For x equal to 1, probability is somewhat lesser. When x is 6, the probability is more. And x is approaching 15, probability is getting near to 0. So it is like normal curve. This blue line is for normal distribution. It's coming up later on. See, next, by using this normal distribution, they will find this curve, normal curve. Both are matching, isn't it? Matching almost. So this is normal approximation of binomial distribution for n is equal to 15 and the probability is 0.4. Now, the normal curve approximation provides a value that agrees very closely with the exact value of the binomial distribution. The degree of accuracy depends on how well the curve fits the histogram. So the degree of accuracy may increase or decrease as n increases. It will increase as n increases. If the sample size is smaller, the accuracy will not be good. So the accuracy of the approximation will be good if n, the size of n is increasing. This is particularly true when p is not very close to half and the histogram is no longer symmetric. Fine. The histograms for binomial and see, two different binomial distribution has been shown. First distribution for sample size is 6 but the same probability 0.2. Second distribution is sample size is 15. Respectively, we will be evident that normal curve would fit the histogram considerably between n equal to 15 and n equal to 6. Let's see what is happening here. This is the histogram for binomial distribution where the sample size is 6. But this is the histogram for n is equal to 15. You see, this is somewhat looking now. This is skewed to the right, isn't it? This is skewed. So when the sample size is more, the histogram may fit the normal curve. it became apparent that if we seek the area under the normal curve to the left, say x, it is more accurate to use x plus 0.5. So some correction factor is being added 0.5 to get more accuracy. This correction to accommodate the fact that discrete distribution, you remember binomial is discrete, and discrete distribution is being approximated by a continuous distribution. Normal is continuous, binomial is discrete. How to get them approximated, how them fit to each other, right? So to fit, we are adding 0.5. Sometimes we will subtract 0.5. The factor 0.5 is called a uniform correction, continuity correction factor. Correction plus or minus actually. Sometimes we will subtract it. The for example, what the reason actually? When you want the probability of x is equal to 10 is possible in binomial distribution. It is discrete, but in the case of normal distribution, there is no property for z is equal to some z1. For x equal to 10, you will find z, but there is no property for z because at z is equal to 1, integration 0. Isn't it? So always the normal table gives property less than z1. It's not equal. Maybe equal to 1, but equality has no role here in this current distribution. So if you want to find probability of x equal to 10 in the approximation normal, we should add and subtract 10.5. We should assume that this is 9.5 less than x less than 10.5, and we should write two z values. Z lies between z1 for 9.5 we will find z1, for 10.5 we will find z2. So z lies between these two, then we can find a property. This is possible in continuous. Straight away equality is not possible, right? This is why this correction factor is sometimes subtracted, sometimes added. Yes. Now, the foregoing discussion leads to the following formal normal approximation to the binomial. The formula comes up. Let x be a binomial random variable with the parameters n and p for a larger n. X has approximately a normal distribution with mu is equal to n times pi, and sigma square is variance, either npq or np times 1 minus p. And this is binomial summation formula for cumulative distributive function of binomial distribution. And this is under the normal curve area to the left of x plus 0.5, including, if you want to include x, you add some points. And so what you get here, this is the formula that we are going to use. This formula, property of x plus, so the same formula, this is like x minus mu over sigma. This is sigma, do not confuse it. npq, q1 minus p is 2. So npq is variance square root of variance is sigma. np is mu here, and x plus 0.5 is replacing the x. That's almost same, isn't it? So this is the formula we are going to get new z value, and then obviously use normal tables to solve the problem. And the approximation will be good if np and n times 1 minus p are greater than or equal to 5. N and when the mu you find is greater than or equal to 5, the approximation will be good. The quality of the approximation is good for larger n's. If probability is close to 1/2, the moderate or small sample size will be sufficient for a reasonable approximation. So either probability will be close to half or n should be larger. Let's start the first example of approximation. What's given here? I think you are slightly understanding what is going on. After 1 or 2 examples, it will be more clear. Coin is tossed 400 times and note down the information. What is given? N is 400. Use a normal curve. See, no property has been given. You should identify. When tossing a coin, there are two possible outcomes, head and tail. So what do you get here? Your success. Heads. They are dealing with the heads. Success is head. So random variable X are dealing with the number of heads. Therefore, what is the property of success small p? Is 1 over 2, which is 0.5. Both are good. N is sufficiently larger and probability is very almost probability is 0.5. So not a near, it's equal to 0.5. So they are good looking. Approximation will be fine, more closer. Now let's find. This is between probability of 185 inclusive. So this is discrete. We have to include 185, 210. So inclusive. What do you mean by inclusive? The normal curve. When you come to the normal curve, assume that 210 is the right side. We don't know where is it. We'll find it, 185 here. We'll take 0.5, add it so that you will follow the next value, isn't it? And we subtract it here. Therefore, a 184.5, you will include a 185 and 210 in the club. So you will find area up to 210.5 and subtract the area up to 184.5 for the values of x. Find results, isn't it? Then this will be your area including this boundary points. Okay. Let's take and remove this part from our files. So here what we have to write is the formula for the formula probability of 184.5. We subtracted 0.5 from the left limit and x lies between this two 10.5. Now for this x value and this x value, find two different z values. The formula of z should be properly written. X, we will find latest x plus or minus 0.5. That has been already done here, so no need to repeat here. Write x. NP. N is given here, property is given here. What is NP? Mu, which is NP. 400 into 0.5, which is 200. So mu is 200. What is sigma? Under square root, n is 400, half will be 100, square root will be 10. So we got mu and sigma. Straight away I can use the formula of mu and sigma. X minus mu over sigma. So Z1, use this x value, 184.5. So 184.5 minus NP. NP is our mu. Mu is 200 over 10. And use your calculator. You will find this one as calculator will give you negative 1. See, 200 is more than 184, so it will be obviously negative 1.55. What is Z2? Second value of x is 210.5. 210.5 minus 200 over 10. So this 10.5 divided by 10 is 1.05 positive. 1.05. See, one value is negative, which is left side of the mu. One another z value is positive, the right side of the mu, isn't it? So the area, this is the normal curve. One value is here is at 1, which is negative 1.5. Another value in the right side, which is at 2, 1.05. Now the question is the area between them. So find the area up to or is to the left of Z2 and subtract the area to the left of Z1. You find the middle area. Isn't it? So we are writing it here. The probability of Z1 is negative 1.55 less than Z less than 1.05. So area left of 1.05 from the table 1.05 left of 1.05. What is the area from positive Z distribution? Should have been that here, right? 1.05. Where is 1.0 is here. 0.5 is in this column. You will get it. 8, 5, 3, 1. First one is 8, 5, 3, 1. 0 point, isn't it? This is the area. Second, negative 1.55. Negative 1.55. Negative 1.53. 0.5. The next value is 0.5. So this is the column. Go to this row and this column. It will give you 0.6, 0.0606. So the left of Z1, the area is 0.0606. So we use these two values, 0.606 for smaller Z and 8.531 for bigger Z, isn't it? Approximation also. Okay, the first value to the left of 1.05, we find 0.8531. To the left of negative 1.5, we found 0.0606. Subtract, your answer will be 0.7925. This is the end of case A. Case A. And remember this n and mu and sigma. Mu is 200, sigma is 10. I'm going to erase everything on this board. To find B, we're going to try B. Okay. We will erase everything. So remember, mu is 200, sigma is 10. Question: exactly 205 heads. Probability of X is equal to exactly 205. In a discrete case, it is possible. In continuous case, we should rewrite this one as probability of subtract 0.5. It will be 204.5 less than X less than 205.5, because in continuity there is continuous function. We cannot say exactly, we cannot integrate, isn't it? And X equals to 0 to 0. So this is the way we approximate equality into the continuous case. Okay, now for every X value, find Z value and then go ahead the same procedure. Let me find Z here. Z for the first X value, which is 104.5. The mu is 200 divided by 10. You get this is actually 204. So more than 200 positive 0.45 when you divide. So this is Z1. What is Z2? 205.5 minus 200 over 10. It will be 0.55. Both are the positive. This is Z1. This is Z2. So this is equal to probability of 0.45 less than, which is, let's say, for 0 less than is less than 0.55. Okay. Now from the table, we have to find the area to the left of uh, this one, which is, you can check the table yourself and make sure that you are writing the right answer. 7088 minus 0.6736, which is the area to the left of this value of z. Now when you subtract this one, the answer is 0.0352. Case B has been done. Case C, fewer than, okay, you should remember only mu and sigma. Everything else we will do, we will find. Case C, again I write here, mu is 200 and sigma is 10. This is the information what we know. Fewer than, x is lesser than 126, or more than, or stands for addition. They are exclusive. What do you mean by this is normal curve? Fewer than, for x is equal to 176, you will find an z here. So lesser than this one. Another, for x equal to 227, you will find another z here, and more than this one. So either this or this. They are mutually disjoint. There is no intersection between them. So addition is possible. And there is no intersection between them. So addition is, we can write this one actually. Probability of x less than 176. So we will write x less than 175.5. Is it clear? And another part we will write probability of x greater than 2 to 7.5. Okay, this is what we are going to do. And for this one, we will find Z1. What is Z1? Z1, x is 175.5 minus the mu is 200 divided by 10, which will be a negative. Negative, isn't it? Negative 2.45. Is it 2 will be found by using this value of x, which is 227.5 minus 200 divided by 10 will get you positive 2.75. So we can further write this equation. One of P of z less than, P of z less than negative 2.45 for this first term, plus, or probability of z greater than 2.75, and we know the table shows only the area for probability of z less than 2.5. So we have to rewrite this one. This area you can find from the table, which is 0.0075 plus 1 minus probability of 1 minus probability of z less than 2.75. Okay, right here first one is 0.0075 plus 1 minus this area can be found to the left of z from the table. It is 0.70. So when you operate all these three terms, you get the final answer as 0.0101. That's the end of case C. And all the results are here in the PowerPoint. You can go ahead to the next problem. The process yields 10% defective items. 10% gives you the probability of success. Small t, 0, and this is n, and it's 100. If 100 items are randomly selected from the process, what is the probability that the number of defectives exceeds 13 lesser than 8? Exceeds 13 lesser than 8, isn't it? So greater than 13 and less than 13. Let's do it. What is mu? Mu is n times p, which is 100 into 0.1, which is 10. If p is 0.1, what is q? Q is 1 minus p, which is 90%, which is 0.9. Therefore, sigma is square root of n times p times q. Square root of 100 into 0.1 into 0.9. You get a square root of 9 and you get 3. So remember, mu is 10, sigma is 3. To get the normal approximation from polynomial, right? Question A says probability of x greater than 13. So find z. 13 minus 10 over 3. Now 13.5. The correction factor 13.5 minus 10 over 3. This should have been 13.5. Which is by using calculator we'll find 1.7. So this is equal to probability. This one is equal to probability of z greater than 1.17, which can be written as 1 minus probability of z less than 1.17. So 1 minus this one can be found from the table to the left of z 1.17 positive z. We'll find the area 0.8790, and the answer is 0.1210 for case A. Case A is done. Case B is coming up. Case B. X is let's go ahead with the case B. That is only this part. Part B. Probability of x is less than 8. Less than 8. It is 7.5. So which is find z. Z is 7.5 minus 10 over 3. You will find this is negative 0.83. So this will be equal to Probability of z less than negative 0.83. From the table directly you can find the area as 0.2033, the end of phase B, and the end of this problem as well. Let's go to the next problem. Third problem, again there are two different cases. One is between 170 and 185. B is slightly different. Read carefully. At least 210, but not more than 210. Lies within 210 and 225. So use the correction factors to get the exact values. That's it. You know the idea, I think. Okay, let me solve it. We have enough time to solve it. Case A. Find probability. 20% of the residents in the US prefer white telephone over any other color. So only two cases, white or other color. Probability for white is 20%, which is 0.2. Obviously, Q will be 0.8, 80%, isn't it? What is the probability that among next 1,000 telephones? So N is 1,000. Therefore, mu is N times P, 1,000 into 0.2, which is 200. And sigma is square root of NP times Q. NP is already 200 and Q is 0.8. You will get square root of this value as 12.649. We got it, mu and sigma. Now start question number 70. Subtract 0.5 here, add 0.5 here, isn't it? So it's quite easy for you now. Probability of 169.5 less than x less than 185.5. We should find two z values. What is z1? For this value 169.5 minus 200 over sigma. Sigma is 12.649, which is negative 2.41. Use calculator and z2 using this form, value of x 185.5 minus 200 over 12.649, and this value by using a calculator you get negative 1.15. So two values of z, both are negative, left side of the in the graph will be equal to, so this is where we find z1 and z2. Write this formula now. z1 is negative 2.41 less than z2, negative 1.15. Use the table, find the area left of this term, negative 1.15, which is 0.1251, minus to the left of this one will be almost extreme left, negative 2.4. The area will be very less, 0.0080. The answer is 0.1171. And now remember this mu and sigma. We will solve case B. What is mu? What is sigma? Mu is 200. Sigma is 12.649. Case B. Now read this one, 210. We will consider as 209.5. This is the correction factor. So probability of 209.5 less than x less than 225.5. Now you read the statement. At least, so it's max more than 210, isn't it? More than 210. not more than 25. So it is less than 200. So x lies between these two values. That's written in different word. Now find z values. Z1 for this value. First value of x 209. 209.5 minus 200 over 12.649. And the answer is, use calculator. You will get 0.75. Check your answer. Z2 for the second value of x. 225.5 minus 200 over 12.649, and this Z2 value using calculator, you will find 2.02. This is Z1. So this property can be rewritten as 0.75 less than Z less than 2.02. Both are positive values over the right side of the name. Using table, find the area left of this Z is 2.02, which is 0.9783, and to the left of 0.75 the area is 0.7734, and the final answer will be 0.2049, the end of this problem. Next we will see the answers are given here. Gamma and exponential distributions. Okay, we have 40 minutes to go. We can finish, I think. Two distributions are commonly used in engineering and science application. These two distributions, gamma and exponential, are still continuous distributions. In some occasions in real life, all the distribution cannot be, all the problem cannot be converted into normal or binomial, for example. There are different occasions which are continuously distributed. So in this cases, we use two different most important distributions called exponential and gamma distribution. And more general is gamma. Particular case is exponential. When you particularize gamma distribution, it becomes exponential. So you don't need to separately study exponential. The formula of gamma will give the formula of exponential. So where they are important, queuing theory, very important. Queuing theory used in telecommunications, traffic engineering, computer science, reliability engineering. We will have some examples. So the two distributions that we are going to study here are gamma distribution and exponential distribution. Okay. So time between arrivals at service facilities and time to failure of components, common parts and electrical systems often are nicely modeled by exponential distribution, which is a special case of gamma. So that's what given there a special case. Exponential is a special case of gamma, and it's a relationship that allows the gamma to be used in similar type problems. The gamma distribution derives its name from the well-known gamma function studied in many areas of this is actually gamma function. Gamma of alpha. Alpha, or sometimes some books will write n. The n, whatever comes inside the notation, will be in the power of x. And there is a kernel of the direction e power minus x dx. See, this is for all alpha greater than 0. Alpha value will not be considered negative values. You can write gamma of n, which is 0 to infinity cos to infinity x power n minus 1 e raised to minus x dx. The question, can you change it as n plus 1? Gamma of n plus 1, what happens? Integral 0 to infinity n plus 1 minus 1. It will be x power n e power minus x dx. This is also good. Okay. So this integration is called a gamma function. These kind of integrations can be easily solved if you know gamma function without integration. For example, if I give you integral x cube e power minus x dx, this is what is it? So generally, if you want to integrate this term, you need to use integration by parts. That will take 3 cycles, right? But very easily count the degree of x, alpha minus 1. This is n minus 1. N minus 1 or alpha minus 1 is 3. So what is n? N is 4, which is equal to gamma of 4. How to evaluate what is gamma of 4? The rule is coming. Gamma of 4 is, see, gamma of n is n minus 1 factorial. So gamma 4 in the previous integration, what is gamma 4? Just 3 factorial. 4 minus 1 is 3. 3 factorial, which is 1 into 2 into 3. The answer is 6 for this integration. For this integration, the answer is 6. How easy, isn't it? So if you know gamma function, certain type of integration can be simply answered. So there is a rule. So this is called a gamma function, and there are some properties of gamma functions given here. The gamma value of gamma function of 1 is equal to 1. And gamma of n is n minus 1 factorial. That is gamma of n plus 1 is n factorial. In other words, the n factorial can be written as n times n minus 1 factorial. So this is coming here. N minus 1 factorial is again written as gamma of n. So gamma of n plus 1 can be written as gamma n times gamma of n. Otherwise, n minus 1. So this is for n plus 1. If you remove 1 here, you subtract 1 here. So gamma of n is n minus 1 times gamma of n minus 1. And again, you can take n gamma of n minus 1 is called n minus 2 factorial. So we can take n minus 2 out and write n minus 3 factorial. You can still continue to simplify this one. This rule is very important. All these 4 rules are very important. We will use them very often. Gamma of 1 is 1. Gamma of half is root pi, square root of 5. And this is very, very important. So the gamma of n is n minus 1 times gamma of n minus 1. What is the gamma of n? How to find the value of gamma of n? Is n minus 1 factorial. Think with this introductory information, we will move ahead to find the formula of gamma distribution. You have 2 parameters here, alpha and beta. X is the random variable. This will be appearing in all distributions. So alpha and beta are the parameters of gamma distribution. A continuous random variable x has a gamma distribution with the parameters alpha greater than 0 and beta greater than 0. Then its probability density function is given by this one. Troublesome. 1 over gamma of alpha and beta to the power alpha in the denominator, and then x power alpha minus 1 e power negative x over beta, where x is greater than 0. X should be positive, otherwise the answer is 0. And this is the formula that we are going to use for gamma distribution. And what is the relation between gamma and exponential? Take it, alpha is 1. Alpha is 1 in this equation. I just remove all that. Okay. Now alpha is 1 in this equation will give you f of beta, x comma beta. There won't be alpha anymore, you see. 1 over gamma of 1. Gamma of 1. What is gamma of 1? We have been given in the beginning. Gamma of 1 is 1. And beta to the power gamma. Gamma power 1. Gamma is 1. So alpha is 1. Alpha is 1. We are given alpha is 1. And x power 1 minus 1 it will be 0. E power minus x over beta. The function becomes, this is 1, this is just beta, this is 1, e raised to minus x over beta over beta. That's it. Just an exponential function. Isn't it? That is why a gamma function becomes exponential. What is this beta? Beta is average. Beta is 1 over lambda. In Poisson you might have seen. Lambda is average. So beta is the average of the random variable. Isn't it? If you know the average, you can proceed with this exponential. If you have only average for the gamma distribution, it means alpha is 1. So straight away you can use this formula. So the formula for exponential distribution is very similar to the gamma distribution, where x is random variable and this is a function of only beta e raised to minus x over beta, where x greater than 0, otherwise it is 0, right? And the variance and the expectation, mean for both the distribution has been given. This is for gamma. In the equation of gamma, put alpha is equal to 1, you will get expectation. Alpha is 1, and beta alone will be the expression of exponential variance. Sometimes we will ask you to find expression and variance of the content distributions, gamma or exponential. You can straight away use this formula. Okay, I think it's time to start exercise problems. Okay, some more instructions. Let x be a random variable. It gives the time until the first event occurs in a Poisson process with the parameter lambda. X has exponential distribution with the parameter 1 by lambda. So there's a connection between Poisson and the exponential. Poisson, the parameter is lambda. Here it's beta, which is 1 over lambda. Here beta is 1 over average. But Poisson distribution deals with average. Poisson is a discrete process, exponential is a continuous process. The Poisson process distribution gives a probability that x outcomes occur in a period time equal to lambda t. The exponential gives probability that one has to wait at least x units of time for the first outcome to occur. That's the difference given here Poisson and exponential. In reliability theory, beta is the mean time between failures of a piece of equipment or of patients. There is a memoryless property. The same property is applicable for Poisson as well. Memoryless property. Let T0 be a positive number. Then, if x has an exponential distribution, what does it say? The real line, you note down. This is the point T0, and when you add this is the point T0 plus T. So this distance is called small t. The probability of x is here greater than this one. So probability of x is here greater than this value, isn't it? Given that it's already greater than T0, it's already here. Yes, probability of x, so probability of x greater than T. That is the probability of x plus x greater than T plus T0 plus T. That is probability x is here. What is the probability that x is here? Given the condition that it is already crossed this mark, isn't it? So this event is already probability of x is known to be here. X has occurred here greater than T0. Isn't it? Therefore, it is the probability of x is greater than T. Its probability of x greater than T will be equivalent to probability of x plus x greater than T0 plus T. In example, we will see some examples. So, memoryless says it doesn't need to have the memory of the past. In other words, if a part lasts at least T0 hours, the probability that it will last at least an additional T hours is equal to the probability that it would have lasted at least T hours in the first place. More precisely, Suppose that a pod has the probability of 0.8 of lasting at least 300 hours. Assuming the bulb is running for 300 hours. The probability for this is 0.80. And suppose that the pod has been working for 100 hours now. Already it has worked for 100 hours. No. Now the question is, what is the probability that in additional 300 hours the probability will work? So the same 0.8, but doesn't mean that it will work for, the probability is same for the bulb to work for 400 hours. It's different. It's different. So that's what given here. Let's move to the exercise 6.40 is the problem number from the textbook. Our problem number 1 from this case. In a certain city, consumption of water is given in millions of liters. Okay, consumption of water follows approximately a gamma distribution. So immediately write the formula of gamma distribution. What is f of x? What is f of x? 1 over gamma of alpha beta to the power alpha times x power alpha minus 1 e raised to minus x over beta. All these are true for x greater than 0. This is the formula for gamma distribution. And we know gamma of alpha, how to find gamma of alpha. Gamma of alpha is alpha minus 1 factorial. Okay. Beta alpha should be taken from the problem. Alpha is 2, beta is 3. Okay. If the capacity, read the problem carefully. If the capacity, what is your random variable? What x deals with? Consumption. In a certain city, the daily consumption of water follows approximately gamma distribution. So consumption of water is your random variable. Consumption of water is the random variable, right? So what is the consumption? If the consumption is more than this number or less than this, but this between these two numbers, kind of questions will come, right? So if the daily capacity of the city is 9 million liters of water, capacity is given 9 million. What is the probability that on any given day the water supply is not enough, inadequate? So your consumption is going more than 9 million. That's the meaning. So what is the probability that the consumption is more than 9 million? That's the question. So already we are dealing with millions, so we don't need to use the million again. The meaning is probability of x greater than 9. Because the question is, what is the probability that on a given day water supply is inadequate? It is not enough, means your consumption exceeds 9 million liters. So consumption is our random variable. X greater, so x greater than 9. Obviously, we will write from 9 to positive infinity. The upper limit is not known for continuous cases because the lower limit is 9 here, x greater than 9. And this function, f of x dx. So integration from 9 to infinity, 9 to infinity. What is gamma of 2? We will find gamma of 2 here. Gamma of 2 is 1 factorial, which is 1. And beta is 3 to the power 2, so 1 over 9 here. X power alpha is 2 minus 1 is 1x, e power minus x over 3. That is what we had to integrate. We had to integrate this one. It's not directly a gamma function. Use this 9 outside. 1 over 9 integral 9 to infinity x into e raised to minus x over 3 dx. Use the method, we call it integration by parts. Integral u dv is equal to uv minus integral v du. This is slightly different from the gamma function we defined, right? Otherwise, we can straightly use the gamma function value. Okay. If there is this x over 3, I can rearrange if you like. Better, you can use this one. This is for that gamma function has been defined for 0 to infinity, what we get here. 9 to infinity. Okay, so we cannot directly use the formula of gamma function. We will do in this method. U is, what is U? U is x and dv is e raised to minus x over 3 dx. So what is v? E raised to minus x over 3 over minus 1 by 3. Now we got uv, so this integration will be uv. This negative 1 by 3, the denominator will be the numerator as negative 3. So u is x, v is negative 3 e power minus x over 3. This is 9 to infinity minus integral v du. V is here. This minus and minus will make 3 positive 3. And e raised to minus x over 3 dx from 9 to infinity. Okay, we need space to solve something to be erased. Let me erase some part. And you don't want the information about random variable, don't want the alpha, gamma of alpha. You can remove all these parts. Now start for top. Okay, let's go ahead. This is continuing here. 1 over 9. In this first part, substitute upper limit infinity. You know, ex is infinity and e power minus infinity will be 0. So 0 times infinity times 0 is indeterminate form. We will not get any result here. Indeterminate form. Leave this space. Okay? You can write indeterminate form. Upper limit is done minus lower limit. Substitute 9. X is 9. So minus 3 into 9 minus 27. E raised to minus 9 over 3 is minus 3. That is for this u v is done. And the upper limit and lower limit is done. Minus or plus 3. Integration of this term, will be again e raised to minus x over 3 over minus 1 by 3. The limit will be from 9 to infinity. And this negative 1 by 3 will be inverted and joining this traverse. Minus 9. I'll erase some more parts. Okay, which is equal to the first part. This will be 1 over 9, 27 positive 27 e raised to minus 3, plus this will be 3 into negative 3 is minus 9, and substitute upper limit e raised to minus infinity will be 0 minus, substitute lower limit e raised to minus 9 over 3 will be e power minus 3. So this will be positive minus and minus. Positive 9 e power minus 3. So 27 plus 9 it will be 36 e power minus 3 over 9, which is 4 times e raised to minus 3. That's enough. You can stop here. 4 into e raised to minus 3. That's the end of this problem. One more problem, exponential case. One more problem, exponential case we will do it. That's the end of this problem. Cancel is here. 4 into e raised to minus 3. Cancel is 0.199. The length of time for one individual to be served at a cafeteria is a random variable having exponential distribution with a mean of 4 minutes. So when it is exponential